I will talk today about the new features of the ship energy systems. At first, just let's talk about the main purpose of this library, or what we think it is. So it's for modeling layouts of ship energy systems. The focus should be on energy consumption, analysis over a long time scale. And we think the important requirements are we want simplified and easy parameterizable physics, but on the other hand, we need a sufficient accuracy for energy analysis. And at the end, it has to calculate very fast. So we want to calculate weeks at a sea in some minutes. So that's the main purpose of this library. And for this, we did some extensions, some new features. One big new feature are new fluids. So we introduced table-based fluids, which are very fast running. They are based on CoolProp data, especially the Helmholtz equation of state and the incompressible backend of CoolProp. I hope every one of you knows CoolProp, which is an open source fluid property library. What is new, or why have we chosen this approach? In the old version of the SES library, the fluid properties were pressure independent, and we said that's not sufficient. So now we have pressure and temperature dependent fluid properties, or if we have a two-phase fluid, we also have pressure and enthalpy dependent fluid properties. So at first stage, we just have short selection of the most needed gases, liquids, and two-phase fluids. I want to show you later. Other features. We have a lot of new components. One important component is the discretized heat exchanger. So that allows us to model also two-phase flow. We can now model evaporation and condensation in a very, very simple way. And on the same way, we also improved the old heat exchangers. We revised these old heat exchangers. Other important components are a fuel tank. We have a new combustion unit, and we also had to extend a lot of components like valves, mixers, splitters, boundary conditions, pumps, and compressors, very important, to the new fluids. So that was my introduction. And now we will have a small hands-on where I want to show you just all these facts I told you. So let's go to SimulationX. What you can see here is one of our new samples. So this sample is called, just have a look, it's fuel gas supply system with pump and vaporizer unit. So what is the idea? We have a ship with a fuel engine, and this engine needs fuel in a gaseous state, but we are transporting maybe LNG. In this case, I just use methane, and we want to evaporate the methane by a heat exchanger just to have a gaseous state of the fuel. That's the main idea of it. And then I added glycol cycle seawater, which you can see here with methane in one heat exchanger. So seawater will be very corrosive. So maybe that's not a good idea to do it directly. So it's really common to have such a glycol cycle. So at first, I want to show you the fluids and how you can see and find these new fluids. One good example is the evaporizer. In this case, we have a heat exchanger for liquids to two-phase fluids. So you can choose your fluid in the heat exchanger. Here you can also see our old fluids. And if you have in brackets something like HEOS or Incomp, that are our new CoolProp fluids. So we also have new models for seawater, for normal water, and we have these glycol mixtures for the liquids. And very interesting, on the other side, we have two-phase fluids. So we have water, steam, and methane and ammonia. So at first stage. What I want to say is, if you have a wish to extend this selection, please call us. It's possible to extend this selection. So I showed you here first the heat exchanger for liquid to two-phase. And if you go to the library tree, you can see we have several heat exchangers. The first 6 are just simple heat exchangers, and the other 3 are discretized. So we just not only have a liquid to two-phase, we have also a gas to two-phase heat exchanger. I just want to show it. Yeah, here you can see also our old fluids I have marked as obsolete. Please be aware our old fluids are pressure independent and the new fluids are temperature and pressure dependent. So it's really a big change. So you have the basic fluids like air or oxygen, nitrogen, just basic stuff. Okay, and these fluids you can use in every component. Sometimes you have the case you have just the pump for liquids. As you can see here, that's a pump just for liquids. And here we have a pump for two-phase fluids. So we have a lot of new components. Okay, so I told you something about the new fluids, and I also started to introduce the new discretized heat exchanger. Yeah, so the name is discretized heat exchanger. We have a cell model for this heat exchanger, which is necessary to model evaporation and condensation. And for this, I have a small scheme for you. It's just a cell model of a counterflow heat exchanger. We neglect pressure drop completely. So it's only parameterized by an efficiency, by a heat transfer coefficient and the area. So very, very easy. And because this is very, very easy, we get a very good performance. What I also like at this heat exchangers is that we can visualize temperature over the flow direction. So I started the calculation. Just give a minute. Just for your information, I'm calculating here 15 days. You can see it's very fast. And also this visualization of the heat exchangers here in this figure. Just let's wait till it's done. Okay, so yeah, just have a look at this visualization. We have on this axis the temperature, and X is the discretization or the flow direction. So the blue line is in our case glycol, and the red line is methane. And I also marked here the flow direction. It's a counterflow heat exchanger. The nice thing you can see here is we have this plateau of phase transition. So we start with liquid methane, and at one point we start to evaporate, and we need a lot of energy to evaporate it. And at the end, we are superheated and we have our fuel. So that's really a significant change to the old version, that we can now model condensation and evaporation of fluids in a very easy way. So just let's go to the whole model. As I already told, we have also some other new components. The storage tank is really new, so you can use it for an LNG tanker to store really the LNG. In our case, we use methane because we have no LNG model, but that's one thing. We have a lot of other stuff I don't want to show you today. Just as last point, just have a look on some results I prepared. Here we have our result window, and as I already told you, we have 15 days of calculation. And this first window shows us the power of the engine. So we have a scenario with zero power and high power. The second window shows our storage tank. So we are really using our fuel, and the level in the storage tank is decreasing. And what is interesting on this library, we have also the energy consumption of the consumers. So I just plotted the energy consumption of this heating cycle pump and also this two-phase pump. And here you can also see how much energy do we need for e.g. pumps. And on the last point, I wanted to show you the heat we need for the vaporizer. Here it is. I just have to zoom. Okay. So you also get an idea how much heat transfer you have to assume in your heat exchangers.